Heavy industry has a decarbonization problem, and hydrogen internal combustion engines are emerging as one of the most viable zero-emission solutions for large-scale power. Look at this hydrogen fuel delivery system. High-pressure gas in a tank passes through a pressure regulator and feeds into a common fuel rail. Attached to that rail are individual gas injectors, the primary mechanical bottleneck holding back commercialization of hydrogen engines. The initial engineering assumption was that we could modify existing high-pressure liquid fuel injectors to spray gas instead. That approach fails almost immediately. The first major failure mode is an extreme loss of pressure. Traditional internal components are bulky. When you force a highly pressurized, low-density gas to navigate around the complex outer geometry of solid shafts and springs, it destroys the flow momentum. The gas loses pressure before it ever reaches the combustion chamber. The second failure mode is severe mechanical impact wear. These injectors slam a heavy metal valve against a metal seat hundreds of times per second. Liquid fuels naturally lubricate and cushion that impact. Gaseous fuels offer zero self-lubrication. Without it, the metal simply hammers itself to pieces. The third and most complex failure mode is hydrogen embrittlement. Standard fuel injectors rely on specific martensitic steels for their internal magnetic actuators. When those specific alloys are continuously exposed to pressurized hydrogen gas, they absorb the hydrogen atoms, become brittle, and rapidly fracture. Solving these three problems requires abandoning the traditional liquid fuel layout. We have to architect a novel injector from the ground up, one that entirely decouples the gas flow path from the mechanical actuation system. Designing a mechanism that independently handles pressure drop, mechanical wear, and chemical embrittlement is the only path forward for reliable hydrogen combustion. We start with the outer body of the injector, sitting right above the engine cylinder, tapering down to a narrow valve seat at the bottom. Next, we drop in the central moving component. Instead of a solid metal rod, we use a hollow pintle shaft. In older designs, fuel has to squeeze past the outside of a solid shaft, navigating tight gaps and causing severe turbulence. By hollowing out the pintle, we can route the highly pressurized gas directly through the exact center of the mechanism. The gas enters through a proximal aperture at the very top of the assembly. It travels straight down and exits through a radial distal aperture, located just millimeters upstream from the valve seat. When the entire shaft lifts off the seat, the high-pressure gas immediately discharges into the cylinder. When the shaft drops, it seals the opening. This internal routing creates a completely unimpeded, straight-line trajectory for the gas. That straight gas passage preserves the flow momentum and neutralizes the pressure drop problem. That clears the first engineering hurdle. To open and close this valve with microsecond precision, the injector needs a heavy magnetic armature and a dense coil spring attached to the shaft. To generate the necessary magnetic field, those actuation components must be machined from martensitic steels. If those highly stressed steel parts touch the hydrogen flow, they will suffer rapid embrittlement and shatter. The solution is a structural quarantine using flexible corrugated bellows. Welded to the outer body and inner shaft, they flex to maintain a fluid-tight barrier. This creates an isolated intermediate chamber on the outside. Hydrogen flowing down the center can never cross. By quarantining the gas to the inner shaft, the external actuation hardware safely utilizes highly magnetic steels without risk of chemical degradation. That leaves the final parameter, preventing the heavy metal valve from physically destroying itself due to the lack of self-lubricating liquid fuel. Because that newly created intermediate chamber is permanently sealed off from the hydrogen, it provides the perfect cavity to house a dedicated low-viscosity lubricating fluid. This diagram shows the magnetic armature suspended inside that fluid-filled chamber, locked to the central shaft. Looking closer, vertical through holes drilled into it connect to a narrow upper section called the plenum chamber. These pathways enable a fluidic braking mechanism known as squeeze damping, which engages right as the valve is aggressively slamming shut. When the spring pushes the pintle upward, the armature acts like a piston, rapidly compressing fluid trapped in the upper plenum chamber. The only escape for that fluid is forcing itself backward, down through those narrow through holes. This fluid restriction generates an immediate high-pressure zone above the armature, actively resisting the upward motion. This hydraulic resistance drastically decelerates the pintle in the final fractions of a millisecond before physical contact.
This squeeze-damping mechanism flawlessly mimics the cushioning of liquid fuels, preventing the valve seat from hammering itself to pieces over millions of cycles. Pulling back to the complete cross-section, we see how this architecture functions as a single unit. An injection cycle begins when the outer solenoid coils are energized. The magnetic field pulls the armature and the attached shaft downward against the heavy coil spring. As the shaft moves, the upper and lower corrugated bellows stretch effortlessly, maintaining the rigid separation between the two zones. With the valve seat open, high-pressure hydrogen blasts straight down the hollow shaft and immediately out into the engine cylinder, without losing its momentum. When the exact fuel mass is delivered, the solenoid cuts power. The heavy main coil spring takes over, aggressively driving the pintle up to close the valve. Instantly, the hydraulic brake engages in the outer fluid chamber, bleeding off the kinetic energy and softening the final impact to a precise seal. What this patent represents is a single mechanical housing containing two perfectly segregated, highly specialized environments. The internal environment is optimized strictly for unimpeded, straight-path gas flow. The external environment is a lubricated, hydraulically dampened, and completely hydrogen-safe haven for complex electromechanical actuators. By engineering away past pressure drops, impact wear, and metal embrittlement, this architecture gives gaseous fuels the exact mechanical reliability required to power the next generation of heavy industry.